What's up? I'm Vin, and today I want to show how to find derivatives of exponent and log functions. So we're going to start out, we're going to find for all these questions, we want to find dy dx. And for the first question here, we're going to look at y equals, and we have e to the cosecant x. And for this question, there's a few things we have to know, but the derivative of e to some power f of x, where f of x is a function, the chain rule variant for this is going to be f prime of x times e to the f of x. So in this question here, if I want to find dy dx, then all I have to do is I'm going to do e to the cosecant x times, and then f prime of x here represents the derivative of the exponent, and the exponent is cosecant x, so we're going to take the derivative of cosecant x. Now let's pretend you forget this formula, because this is a very easy one to forget. When I want to take the derivative of cosecant x, I'm taking the derivative of 1 over sine x, which is the same thing as sine x to the negative 1. So then this becomes negative 1 times sine x to the minus 1, which is minus 2. And then the derivative of the inside is cosine x. So I'm just using chain rule. The derivative of the outside, I use power rule, and then keep the inside the same, times the derivative of the inside is cosine. And then if you rearrange this is going to be minus cosine x over sine x squared, which is the same thing as sine x times sine x. So if I extend this fraction and I put the invisible 1 here, notice minus cosine over sine is the same thing as minus cotangent. And then 1 over sine x is the same thing as cosecant. So the derivative of cosecant is minus cotangent cosecant. But if you just have that memorized, then awesome, just use that. So the derivative of cosecant I'm going to write first. We have minus cotangent x, cosecant x, and then we have times e to the cosecant x. So here's our derivative for the first example. So let's say next for question 2, we're going to now take a derivative of y equals e to the square root x. So once again, we have to know that the derivative of e to some power is going to be e to the same power, and then we have the derivative of the exponent, which in this case is square root x. Now when I think of square root x, I think of x to the 1/2 power. So that way I could do power rule. So our derivative here is going to be e to the square root x times, and I do power rule, and I get 1/2 x to the minus half. And then if I just do a little bit of algebra and make this look nicer, in the numerator I'm going to have e to the square root x, and in the denominator I have a 2, and then x to the minus half is the same thing. So x to the minus half is the same thing as 1 over square root x. So the square root x is going to go on bottom also like this. And that's our derivative to question 2. For the third question, let's take a look at, we have y equals 5 to the negative 2x. So for a question like this, we have to know the derivative of a to the f of x power, where a is some positive constant. So we have a is greater than 0, is going to be equal to, and we're going to have a to the f of x times natural log of the base, which is a, and all of that times f prime of x. So if we just know this formula here, then this question is not too bad. So dy dx is equal to 5 to the negative 2x times natural log of the base, and then we take the derivative of the exponent, which in this case is minus 2. So there's a few ways that we could deal with this. You could leave your answer like this, but if you want to combine stuff, what you could do is you could take 5 to the negative 2x, and the negative 2 times natural log 5, I think of negative 2 natural log 5. I could send that back in as an exponent and make this 5 to the negative 2. So then I have natural log of 5 to the negative second. And if I want to simplify it even more, I could leave my answer like this, or I could make this 1 over 25 on the inside. So once again, if it's not specified, we could stop here. But if we want to simplify or make this stuff positive exponents, I could say something like natural log of 1 over 25. And I could send 5 to the negative 2x down as 5 to the positive 2x. So this would be if you just wanted all positive exponents here, that this is okay. But otherwise, stopping here is fine. So for the fourth question, let's look at, let's say we have y equals, and we're looking at 2 to the cosine 5x. So let's say I forgot that formula from before. And if you ever forget that formula from question 3, you could take the natural log of both sides, and you'll get natural log of y equals natural log of 2 to the cosine 5x. And then exponents you could bring to the front of the log. So anytime you have something to a power inside of a log, that could go in front as an exponent. So that's just properties of logs. So, and you have cosine 5x times natural log 2. But then this idea comes into play. Anytime you take the derivative of a constant times a function, you get k times f prime. And in this case, k is equal to natural log 2. And a lot of students get thrown off by that even though this has a log attached to it, a natural log, this is still a constant. So I could think of this as natural log y equals natural log 2 cosine 5x, and then this is like in that shape, k times f of x. So now we're going to take the derivative of both sides with respect to x. And on the left side, I have to use implicit differentiation. I get 1 over y dy dx equals, and I leave the constant alone. Natural log 2, I don't do anything to because of this formula. And then the derivative of cosine is negative sine. I keep the inside as 5x, and then I multiply by the derivative of the inside. So I multiply by 5. And now from here, if I want to solve for dy dx, we just multiply both sides by y. So then dy dx, if we start to write this out, the right side is going to be negative. I'm going to have negative, the 5 I'll write in front, and I have natural log 2. Then I have sine 5x, and then I have y, and y is equal to 2 to the cosine 5x. So this entire expression here is our answer to question 4. Question 5 and 6 we'll look at next to each other. So let's say for question 5, I have y equals, and I have x to the pi power. And then for question 6, I have y equals pi to the x. So for something like this does throw students off, but just know question 5 is a power function, and question 6, you have an exponential function. So anytime you have x to a number power, the derivative, you just have to use power rule. And this is going to be pi times x to the pi minus 1. A common mistake for question 6 is people do the same thing and they say x times pi to the x minus 1. But for question 6, you have to know when you have the derivative of an exponential function like this, where a is positive, this is going to be a to the x natural log of a. So dy dx is just going to be pi to the x natural log of pi, and we stop here. We could do the implicit differentiation that we did in question 4, but knowing this formula saves you a lot of time. So for question 7, let's say we're looking at a natural log function. We have y equals natural log of x to the third. Now for this question, there's a pretty convenient shortcut. If we do the algebra first, we could bring that 3 out as 3 times natural log x. And then when we take the derivative here, we're just doing 3 times the derivative of natural log x is 1 over x. So this simplifies to 3 over x. And if you wanted to, you could use chain rule here. You could say, I'll write it as dy dx equals, you could do 1 over the inside times the derivative of the inside, and this would still simplify to 3 over x. Okay, so using the algebra works, or also knowing this formula. When you take the derivative of natural log of a function, you have the derivative of the inside divided by the inside. So this is a nice little shortcut, but the algebra is a little bit of a nicer solution. So for question 8, let's say we have another natural log function here, and we have natural log of this time 10 over x. So I could do chain rule here, but once again, I think it's easier to try to do some algebra. And I could split this up as natural log of 10 minus natural log of x. So we're just using log properties here. And then from this step, I could take the derivative of both sides. And the derivative of the left side is just dy dx. And the derivative of natural log 10, this is a constant, so the derivative starts out as 0 minus, and then the derivative of natural log x is 1 over x. So the derivative here is just going to simplify to minus 1 over x. For question 9, let's say we're looking at y equals, and we have log of x to the 5th power. So once again, we could start this with algebra and just say 5 times log of x. But another useful formula here for us is that when I have log base a of x, and a is greater than 0, knowing the change of base formula, natural log of x over natural log of a, is going to make life very easy. We could prove this formula, but it helps to just know it. So what I want to do in a situation like this is I'm going to rewrite this. Just know, technically, what I think about for a question like this is that log of x, the invisible base, is 10. So when I'm writing natural log of the inside over natural log of the base, just keep in mind that a represents the base. So I'm writing 5 times natural log of x over natural log of 10. But then the next little bit of algebra I'm going to do is I'm going to group 5 and natural log 10 together. I'm going to write 5 over natural log 10 times natural log of x, because then once again is this idea: the derivative of a constant times a function is the constant times the derivative. So when I take the derivative to close this out, I'm leaving the constant 5 over natural log 10 alone. As wacky as this looks, that's our constant. But I'm going to just do 5 over ln 10 times the derivative of natural log x is 1 over x. So then this gets simplified to 5 over, and it's better to write the x in front like this, but 5 over x ln 10. Now for question 10, I want to look at y equals log of e to the x. And for something like this, once again, I'm just doing the algebra. I'm going to bring the x out, and I'll have log of e. And just note, log of e, this term right here, is just a constant. So this is one of those derivatives that's so easy that it's difficult. When anytime you take the derivative of, let's say something like, let's say it's just 12x. The derivative of 12x is just 12. So when you take the derivative of something linear, something like mx plus b, where m and b are constants, the derivative is just the coefficient of x. So technically here it's a little bit out of place, but the coefficient of x is just log e. So I could just say it's something like 1 times log e, or just log e. So this is going to be our answer to 10. Now one thing, if you solve this an alternate way, some people might opt to do a change of base here, but just know log of e works out to natural log of e over natural log of 10, and natural log of e is equal to 1. So if you solve this an alternate way, you could also get the answer 1 over ln 10, but log e is sufficient for our answer. Now for question 11, we're going to find the derivative of log base 2, and then we have square root of x plus 1. So for this, I'm going to start by doing a change of base formula. So we're going to have y equals natural log of the inside over natural log of the base. But we'll do a little bit more algebra. Just know that square root of x plus 1 is the same thing as x plus 1 to the half power. So what I could do with that is I could rewrite this as natural log of x plus 1 to the half divided by natural log of 2, and that 1/2 could pop out in front. So now this is 1/2 natural log of x plus 1 over ln 2, but then from here I could separate things. 1 over 2 divided by ln 2 is just 1 over 2 ln 2, and this is going to be multiplied by natural log of x plus 1. So just doing a little bit of algebra, we could rearrange it to this, but the benefit of doing this, once again, is we're using the idea that the derivative of k times f of x is k times f prime of x. So our k value here is 1 over 2 ln 2. So then dy dx, we just leave this alone, the constant, and we multiply by the derivative of natural log x plus 1 is 1 over x plus 1. Technically, I could do the chain rule here, but the derivative of the inside is 1, so I could just leave it like this. And I could leave my answer like this, but a little bit of nice algebra we could do is we could send that 2 back in as an exponent, and we'll get 1 over natural log of 2 squared, or natural log of 4, times 1 over x plus 1. And if we simplify this into a single fraction, this is 1 over ln 4, and then times x plus 1. So for question 12, we'll take a look at this function. We have y equals 1 over, and we're going to have log base 4 of x. So for something like this, we'll do change of base, and we'll write the denominator as ln x over ln 4. So we're doing natural log of the inside over natural log of the base. And then this flips to ln 4 over ln x. But I could do quotient rule here, but if I could avoid quotient rule, that usually makes life easier. So I'm going to send ln x in the denominator up as ln x to the negative 1. So now the derivative, this is just a constant. So I have negative 1 times ln 4 is negative ln 4. And then in the parentheses, I have ln x to the negative 2. So I'm just doing chain rule here. I have the derivative of the outside. I keep the inside the same, and then I take the derivative of the inside and multiply. So what we have here is dy dx is equal to, and in our numerator, we're going to have negative natural log 4 over, and then we'll have x times natural log of x squared. Be mindful here that I can't just write the 2 next to the x, that the entire quantity ln x is being squared. And this is going to be our answer here to question 12. So for question 13, we'll take a look at y equals x to the 1 minus e. So even though it has an e attached to it here, this is a power function. So to take the derivative, we're just going to do power rule. So we bring the power down, 1 minus e x, and then we subtract 1 from our old exponent. And notice 1 minus 1 cancels here. So the derivative is going to be 1 minus e x to the negative e. And if I want to write this with all positive exponents, I could just say that our derivative dy dx is equal to 1 minus e over x to the e power. So for question 14, we're going to have y equals, and we have natural log of 2x in parentheses to the third power. And for this, we could just use chain rule. And we got to do the derivative of the outside using power rule. We keep the inside the same, and then we multiply by the derivative of the inside. And the derivative of natural log of 2x, we have 1 over 2x times the derivative of 2x, which is 2. Now just know there is an alternate way of doing this. You could have expanded the inside to natural log of 2 plus natural log of x to the third, and that might make the chain rule step a little bit easier. But ultimately, you're going to get the same answer, so we could just take the derivative of the first one. Now here, 2 over 2 is going to cancel. And if we package this up into a single fraction, we have 3 times parentheses natural log of 2x squared, all divided by x. So here's our derivative to question 14. All right, so last question here. Let's take a derivative this time of y equals x to the ln x power. So what we're going to do here is we're going to take the natural log of both sides. So we have natural log of y equals ln x to the ln x. And now exponents inside of a log could go in front. So we'll have natural log of y equals ln x times ln x. But this we could repackage as just natural log of x to the second, but the whole thing in parentheses squared. So now at this step, we could take the derivative with respect to x. And we're going to use implicit differentiation. So the derivative of the left side is 1 over y times dy dx. And the right side, we're going to use chain rule. So we have the derivative of the outside using power rule. We keep the inside as natural log x. I could write a 1 here, but an exponent 1 we don't need. And then we multiply by the derivative of the inside. So now if we bring this over here, we have 1 over y dy dx equals, and I'll simplify this, this is 2 natural log x over x. And what we're going to do here is we're going to just multiply both sides by y. And then these terms are going to cancel. Now the 2 here I could send back in as an exponent. So this is dy dx equals natural log of x squared over x. And then instead of y is equal to x to the ln x. Now if we leave it like this, it's a little bit sloppy. Just know old algebra rules, a to the b divided by a to the c is a to the b minus c. So this is just old algebra. So here, x to the ln x divided by x to the first, I could combine by subtracting exponents. So I would have natural log of x squared at the end, but then in front I could say x to the ln x and then minus 1 like this. Okay, just know it's not natural log of x minus 1. It's natural log of x, that whole quantity, and then minus 1 there. So I'll make a little bit of space so it stands out more. So I would have x to the natural log of x, and we leave a little space, minus 1. And then that takes care of these two. And this is all multiplied by natural log of x squared. So here is our solution to the last example. Okay, well, this is going to conclude this video on taking derivatives of exponent and log functions. If this video was helpful, please like and subscribe. It really helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comments section below. And thanks for watching.